So as we're talking about torsion, there's another important related quantity that we can derive from all of the equations we've been discussing so far. So if we think about torsion, some of the things we've talked about are our shear stress, right? Our shear stress is a relationship between the torsion, and it can be a linear function. You know, if you have a changing torsion or you have changing geometry, it might be torsion related to x, times rho over the moment of inertia, which again, we could relate to x if we have like some changing geometry, right? Maybe something starts thinner, gets fatter, something like that. We could have a changing geometry here. We also had the relationship of the angle. So as the angle changes, we said that was related to shear strain, dx over rho, right? Where this angle here, this initial position and then final position, okay, this angle here, it's phi for any given dx that we're looking at. And then we also have the relationship of our shear stress and strain, right? We can relate these two together with our shear modulus of elasticity, G. So we have all of these formulas we can use to talk about torsion, describe things. We can also use our power transmission formula, our power formula, to talk about torque and our rotational movements. Right, so if we start combining some of these things together, right, I have a rho in this equation, I've got a rho in this equation, I could make a substitution in here, where I have the shear stress is my torque, times, now instead of my rho, if I do that substitution, d phi over gamma dx, j, our polar moment of inertia. And I can go ahead and make another substitution in for my gamma here. I could say my shear stress is that torque, polar moment of inertia, d phi over dx, and then that gamma, I can make that into I'm actually going to set this equal. I'm going to put gamma in here, and I'm going to say instead of this T, this tau, this tau shear stress, I'm going to say this equals G times gamma, because what that'll let me do is cancel out my gammas so that I can rearrange this equation and solve for that angle of twist. This angle of twist here, that's represented by this torque, this rotational movement, means that it had some initial position and is now twisted by whatever degrees it is, or I guess whatever radians it is. I can rearrange, solve this. I get d theta is t of x dx over jx g x, I guess, if it was a changing modulus of elasticity. And what this gives us is this handy angle of twist equation as an integral over 0 to the full length of our torsion dx over polar moment of inertia of x times shear modulus of elasticity dx. And this guy might look kind of familiar, right? He's super similar to our axial load displacement equation, right? Our axial load displacement equation was delta is PL over AE, right? Our load times the length over area times modulus of elasticity. So for something that's held constant, our angle of twist, if we have constant torque and a constant cross-sectional area, same shear modulus of elasticity, we would get TL over JG. Torque times length over polar moment of inertia times shear modulus of elasticity. So you can see it looks very similar to our load displacement equation that we had in axial load. Right, so our axial load displacement equation looks super similar. Right? We have this very similar relationship with angle of twist. Angle of twist, where you have torque times length over polar moment of inertia times shear modulus of elasticity. Right, where now just instead of a load, you've got a torque. Instead of area, this geometric quantity is represented by the polar moment of inertia. And you're given your angle of twist in radians. And it kind of makes sense, right? When we're looking at some beam here, some rod, I should say, some rod that's subjected to a torque, some rod that's being twisted, it's initially sitting at this position straight up, and then as it's twisted, it goes through this movement, right? Goes through this movement to make this angle phi. So it's kind of like a displacement, just your displacement is a twist instead of a moving backwards or forwards, right? It's a twist. So we represent this twist by the angle, and this is our angle of twist. That's what this phi represents. This is angle of twist. Again, this is the one we'll see most commonly when we have a constant torque or constant cross-sectional area. But just like we did in axial load, we can use this integration form here. And we can also use it to break things into parts and sum those parts together. So if we had something with several cross-sections, or several torques, or several a changing polar moment of inertia, things like that. We had torque 1, and then here's torque 2. We can do the same thing where to get our angle of twist, we can just sum up the torques for each location. Right, breaking it down into sections and then summing them up. And we'll work an example so you can see how this works, but it's very similar to our axial load applications. Just the difference is that instead of looking at force loads, we're primarily looking at moments. That's the key with this, is that now instead of those axial forces, axial loads, where we were looking for F, now because it's a rotational movement, we're looking at the M. We're looking at moments instead of forces. And one key thing I want to note here is the sign convention on these things. So whenever we're doing our sign convention on a rod, we're kind of breaking that up, opening it. Let's say here's a rod. And we want to look at the moment sign convention. What we do is we use the right-hand rule. And our right-hand rule states that we point out from our cut, and the direction we curve our fingers in is the positive torque. The positive torque and the positive angle of twist. So if I were to grab the rod on the right, I grab the rod on the right, I guess the way I am looks a little bit flipped around. If I grab the rod on the right and I point my thumb out from it, and I curve my hand around that rod. So here's my hand. I point my thumb out. And so the rest of my fingers curve around the top of that rod. If I were like grasping the top of it. There are my little digis, my grippers there. Right, so my thumb points out. And then the direction that my fingers go over the rod, this is the positive direction for torque. And it would be your positive angle of twist as well. So this angle here, you'd go straight up, and then it juts out to the back like that. That would be a positive angle of twist. And same with this other side. I would point my thumb outwards, my right hand thumb, that's why we call it a right hand rule, point my right hand thumb in the direction outwards from that cut, wrap my fingers around, and this is the direction of the positive torque, right? All of these little guys represent my fingers. This is the direction of the positive torque. Where now my angle of twist originally starts upright and moves out this way towards us, right? Coming towards us, that's my positive angle of twist. So just remember your right hand rule, thumb points out, and then your fingers give you the positive direction of the torque. That's our sign convention for these. Let's take a look at some example problems. So this example says, and sorry, my chicken scratch handwriting is a little extra chicken scratch right now, but it says, a rod with a diameter of 12 millimeters must withstand a twist of 180 degrees without exceeding a shear stress of 300 megapascals. If our shear modulus of elasticity G is 80 gigapascals, what's the minimum length required? So we can use that relationship that we just learned, right? Our angle of twist relationship. If we go ahead and write that equation, just for our reference here, TL over JG. And it just says a rod, like we're just going to assume that it's a constant rod, right? A rod with a constant 12 millimeter diameter. Gives us our shear stress, our shear modulus of elasticity, and we're trying to find this minimum length required. So if we look at our recipe here, right, in our recipe, we have an angle of twist, torque, length, polar moment of inertia, and shear modulus of elasticity. So the ingredients that we've already got in our problem statement, we know G is 80 gigapascals, which a giga is 10 to the 9th, right? Giga is 10 to the 9th, mega is 10 to the 6th, kilo is 10 to the 3rd. So 10 to the 9th pascals. So we've got one ingredient to put in our recipe there. Length is what we're looking for, so we don't know length. So length, don't know. Torque. Our torque, we also don't know, but we've been working with our torque equation, right? We have that relationship for torque. We can get from our shear stress is torque times the outer radius over J. So we can back calculate our torque from this because we're given our shear stress of 300 megapascals. So that's again 300 times 10 to the 6th pascals. But the last thing we're missing in our recipe here, the last ingredient we need, is polar moment of inertia. Right? We've got to calculate our polar moment of inertia, which it doesn't say, but it says a rod, so we're going to assume that that is a solid rod. And for a solid rod, our polar moment of inertia is pi over 2 times r to the 4th. So we can calculate this because it did give us our diameter of 12 millimeters. So our polar moment of inertia is pi over 2 times 0.006 to the 4th power. Right, all I did was take my diameter, divide it by 2, so that gave me 6 millimeters, and then converting that into meters gives me the 0.006. And then I just pop that into my calculator. Right, stick it in the microwave, make it ready for our recipe here. And that's going to give me 2.04 times 10 to the negative 9th meters. So now this is extra handy because I can use this in two places, right? I'm going to use it in this shear stress equation, and then it's also an ingredient for my recipe overall up here. So let's go ahead and take this guy, our shear stress equation, and calculate what the torque is. So our torque, if I just rearrange this equation, is the shear stress times shear modulus of elasticity over the outermost radius. And we want the outermost radius because they give us that max shear stress, right? So I'm going to go ahead and plug all of those things in. It gave me shear stress 300 times 10 to the 6th. My polar moment of inertia 2.04 times 10 to the negative 9th. And then my outer radius is 0.0, whoops, okay, I don't know where that disappeared to, but 0.06. 0.06. Pop that into the calculator, and we get a torque of 101.8 Newton meters. So now I've got the gang's all here, right? Got the torque, I've got the polar moment of inertia, I've got, who else do we have? There we go. Shear modulus of elasticity. And who are we missing? We're missing L, right? We're looking for L, but our problem statement did give us the angle of twist here, right? A twist of 180 degrees. So 180 degrees equals pi radians, which is important because phi is always going to be in radians. So I'm going to rearrange this equation to solve for length. So our length is going to be phi j g over torque. Plugging everything in, that gives me pi, right? Our angle of twist is pi radians. That torque value was 101.8. Whoops, sorry, that goes on the bottom. That's not what I want here. I want J, I want polar moment of inertia. 2.04 times 10 to the negative 9 times shear modulus of elasticity, 80 times 10 to the 9th, then over my torque. So that torque value we just found, 101.8 Newton meters. Right, so I put everything into my base units so that way I know everything is going to work out. Right, you don't want to get here and have a whole mess of unit conversions. Try to convert all of your units as you're going, keeping them in the standard units, because it'll really, really screw up your math here at the end if you've got 10,000 things to punch into the calculator. And when I do punch this into the calculator, I get a length of 5.03 meters. 5.03 meters. And I can twist 180 degrees. That's halfway around. That's a fairly large angle of twist. And 5 meters is, what, like 15 feet? That's not a very long rod to do, you know, a half rotation, essentially, in this angle of twist. So if we think about it, it is a lot like a displacement. It's this rod is able to rotate, right? Rotate in space by 180 degrees given these conditions. And we can go and use our other equations, our torque equation, shear stress. These other equations can be used still in conjunction with our angle of twist equation to find what we're looking for. Here we've got one more example. It says if a helicopter engine delivers 600 HP to the rotor shaft, that's this shaft here in yellow, when the blade is rotating at 1200 revolutions per minute, shaft is 2 feet long, made of L2 steel, determine the diameter of the shaft to the nearest 1/8 inch if our allowable shear stress is 8 KSI and the angle of twist is limited to 0.05 radians. So right off the bat, the first thing that we're going to encounter is that we have two limiting cases here, right? We're limited both by the shear stress and by the angle of twist. If we look at each of those equations, our shear stress is that torque times the outermost radius over the polar moment of inertia, and our angle of twist is torque times length over polar moment of inertia times shear modulus of elasticity. Because both of these equations have this polar moment of inertia, which is inherently based on the radius, both of them will have different answers because they are two different equations. They are two different limiting factors here. Allowable shear stress of 8 ksi, and angle of twist limited to 0.05 radians. So we're going to need to check both cases to see which one is the limiting factor that's going to give us the diameter of our shaft. So let's look at what else this problem gives us. So it gives us the RPM and power here, which automatically tells us that we're going to be needing to use our power transmission equation, right? They give us that our power is 600 HP and that it's rotating at a frequency of 1200 revolutions per minute, which is great that they gave us this because that makes it really easy to calculate our torque, right? Again, with this power transmission stuff, really the key thing is knowing when to use this equation, right? Knowing that this is the equation that you want to use. And then getting the units right. The units can be a real pain because we love putting everything into horsepower. That's what you see things rated at. That's what's going to appear on your problems. You're going to have to know that 1 HP is 550 pound-feet. It comes up all the time. You're just going to have to know it for this class or put it on your note sheet, just wherever you can to remember that 1 HP is 550 pound-feet. It comes up all the time. Or pound-feet per second, sorry. Pound-foot per second. So we're going to want to convert this before we come and get all deep in the torque business. So 600 horsepower, convert this 550 pound-feet per second is 1 HP. And then do I want to convert? I probably want to convert to inches because I have a feeling, let's see. Yeah, I want this to the nearest 1/8 inch, and my allowable shear stress is in KSI, so I don't want to leave this in feet. I want to go ahead and convert this to inches, so we'll do that while we're here. Just since we're messing with units and everything. 12 inches per foot gets my units to cancel out. HP, HP. So I end up with... Oh, I didn't actually calculate it. Where's my calculator? All right. Looking at my calculator, 600 times 550 times 12. That gives me 3.96 megapounds. That's not actually what I want. I want to say 396,000 pound inches per second. Pound inches per second, which is not a super useful unit as is, but it's useful for when we're calculating this stuff, right? If I want to calculate my torque, I can rearrange this so that I have power over 2 pi frequency. I have that 396,000 pound inches per second over 2 pi, and then the frequency that I need here, I want in revolutions per second, because I have this per second term on top. So they give me 1200 revolutions per minute, and there are 60 seconds in a minute, so I just want to divide that by 60. So 1200 divided by 60 is 20 revolutions per second. And that gives me my torque value of... What? I didn't calculate any of this, apparently. It's not on my... Normally I have notes written out in front of me so we don't have to do the calculations, live in New York. It's Saturday night. But I've apparently dropped the ball on that. All right. Divided by 40 pi. We get a power value of not a power, a torque value of 13512 pound inches. Pound inches. That's what our torque is in, pound inches. It's fine. He's just going to come up here. All he needs to do is get plugged into these two guys. That's really all we needed him for. All that work just so we could actually solve the equations that we're interested in. Because we want to know the diameter, right? Looking for this diameter. So our radius comes in our C portion here. This is a radius. J, polar moment of inertia, has radius in it. We know our shear modulus of elasticity. It tells us this is made of L2 steel. So we can go and look up in our handy dandy chart, or handy dandy table, that our shear modulus of elasticity, I'll spare you the table searching. Shear modulus of elasticity is 11 times 10 to the 6th pounds per inch squared, pound per square inch. So we've got the G. It was L2 steel, just looked it up in the table. Length they said it was a 2-foot long shaft. And then we found the torque. So we have all of the ingredients that we need. We're just going to be solving these for the radius. So let's look at our shear stress first. Our shear stress equation. Check if this one is limiting. So we're just gonna get rid of all of these power calculations. We're all done with them. We don't need them. I do want to keep that torque value though. Let's put you over here. And find our, do it in blue here. If our shear stress is limiting, shear stress is torque C over J. This is a solid shaft. I believe it says that. Helicopter engine, it just says rotor shaft. Usually it'll say something is tubular if it's not just a solid shaft. So just assume it's a solid shaft if you're not given any more information. Since it doesn't say tubular, it just says shaft, I'm just going to assume it's a solid shaft. And what was that? Allowable shear stress is 8 ksi. So 8 ksi, or if we convert it to pounds, 8,000 pounds per square inch is going to be 31512, that's our torque, times the radius we're interested in, over pi over 2 r to the 4th. If I do a little bit of number rearranging here, I can get that my r is the cube root, right? My r cubed, I can take a cube root from simplifying this. My r cubed, I'm going to take a cubic root of 31512 over pi over 2 times 8,000. Pop that into the calculator, and we get 1.359 inches. 1.359 inches. So that gives us a radius. We're looking for a diameter, so we know we can just double it. But for now, let's leave it and let's look for the other case, the other limiting factor, if the angle is the limiting factor. If angle of twist is limiting. Here we have our angle of twist is torque length over polar moment of inertia, shear modulus of elasticity. Our angle of twist they gave us is 0.05 radians. So I might actually rearrange this one first before we start plugging numbers in. So this is yeah, we'll go ahead and write this. This is TL over pi over 2 r to the 4th g. So if we solve this, r to the 4th is TL over pi over 2 g b. So now I'll go ahead and plug everything in here. I'm taking a quadratic root, 4th power root. A button in your calculator is going to be a pain to find, but that's fine. Our torque value, 31512, times our length. What was it? 2 feet, I believe, which I'm going to convert to inches. It's 2 feet, but it's 24 inches. Just to keep our units consistent. Pi over 2 times, we pulled that shear modulus of elasticity value. 11 times 10 to the 6th times 0.05 radian. Oof, what a mouthful to put into your calculator. Gives us a radius of 0.967 inches. Right, so remember that these are the minimum acceptable radii. Each of these is the minimum acceptable that can handle this shear stress. If you go with a larger radius, it's going to be able to handle more. So these are the limiting cases. These are the minimums, which means you want to go with the larger value. Right? So this is the limiting factor. The limiting factor is your shear stress because it has that higher radius. It demands more. It requires more. So this is the limiting factor here. But I didn't actually answer the question. I shouldn't have boxed that because I know they were looking for a diameter. Oops. Let's make a diameter to the nearest 1/8 inch. And then we'll have our actual answer. So again, our diameter is the same as 2r, so we double this. And that's going to give us 2.72 inches. And then it wants it rounded to the nearest 1/8 inch. So again, we have to go up higher because this is a minimum requirement. So the diameter for our shaft would be 2 3/4 inches. You'll see it listed like this as opposed to the 2.75, right? It's 2 3/4 inches. 2 3/4 inches. I don't know why this way of writing it out always annoys me a little bit, but this is often how you see it if you were to go to Lowe's or Home Depot and buy the shaft that you need. This is the nomenclature you would see. So this is why you'll see me write it like this, even though I personally like writing 2.75 inches. Just know that in engineering terms, you'll often see it as the way you would buy it off the shelf. So that's it. That's our problem, right? This is our combining everything we've learned about torque so far with this idea of the angle of twist that is kind of like your displacement, and having problems combining all of these ideas, the power transmission, the torsion, the angle of twist, all of these ideas coming together to help you solve problems.